Hello YouTube, welcome back to part 3 of the self-driving car series, and in today's episode we are going to be creating the genetic algorithm script that is going to train our network to perform better over time. So this is where we left off last time. We have a neural net just with random weights, and it's just doing random stuff. So if I play this, the weights are being randomly generated every time it crashes into the wall, and it's just gonna restart and randomize the weights again. So yeah, sometimes it performs really well for no reason. Just gonna hope this crashes. No. Okay, so this is solve the course. There we go. So if you can see, if it crashes, it randomizes, and as we saw last time, sometimes the neural net performs so well randomly that it actually completes the course. That actually kind of shows that this course is a bit off, like it's a bit too easy for the network, and to get proper results for the neural net, we'd have to make this course a bit harder. So one mistake I made when making this course is only incorporating mostly left turns and straight turns. There isn't much right. I tried to add it here at the turn. This is where most cars will fail, because there's a right turn and all the cars have learned how to do left turns. So something you'll notice is when working with evolutionary algorithms such as like genetic algorithms, you need to actually incrementally train these networks correctly in order to get the best results. So this is a mistake that I've made, but I'm sure later on you can go ahead and change the course, but this will work for us right now. And another thing that I won't be covering in this series but would be fun for you guys to do is to take the neural net class and actually parse it. So serialize all the values of the weights and biases into a file, and then you can save the best performing car, and then you can try it out on different courses, and that I think would be really fun. And that's where you get into the ability to train one network onto multiple courses, and I think that would be very interesting to try out. But before I talk anymore, let's get into actually coding the genetic algorithm script. Before we do that, let's open up the car controller and neural net class, because we need to get rid of a few lines that we added last time that we don't need anymore. Okay, so let's go down here, go open up the car controller as well. Alright, so one thing, these test code ones, let's get rid of these. Test code, and I think that's all the test code. So the first thing we need to do is create a new genetic algorithm script. So how this is going to essentially work is we're going to have a population. I explained most of this in the last video, so I had a diagram and stuff, but we're going to have a randomly initialized population of say 200 cars. And then we're going to incrementally go through the population every time this car crashes into the wall. Alright, so let's go ahead, create a new C# script, and let's just call it genetic manager. Alright, now once we've created the genetic manager script, before we do anything else, let's create an empty game object. Let's call this manager, and just drag this to the top, and let's create a genetic manager script. Alright, now let's get down to coding this thing. Alright, so first, like usual, we're going to set up all the variables. So let me just open the script, and we need to use MathNet because we're going to be doing a bunch of matrix stuff in here as well. So let's go using mathnet.numerics.linear algebra to bring in the matrices, and let's start initializing some variables. Okay, so the first thing we need is a reference. So we just need a reference to the car controller, and we need some variables to control the actual genetic algorithm. So we need an initial population, and one good value that I found was 85. We need a mutation rate, and these are all values that I found that worked well in my testing. And remember, the mutation rate is the chance that the network will be randomized, so that we're not constrained to the initial population that was created. Alright, now we need control over crossover. So what crossover is basically how, in what method, the two parents of that are selected to breed, the two parents, how they're actually combined, and what networks are combined. These are the controls of the crossover. So we're going to call this best agent selection and worst agent selection. So what these two are is, it tells you, all right, let's pick 8 of the best cars that performed and 3 of the worst cars that performed. So this is the thing with genetic algorithms. You have complete control over what cars you want to, what cars you want to pick from the population, how you want to pick them, which ones you want to breed, how you're going to mix up the weights. You have control over all of these little elements, and that's what makes a genetic algorithm so, usable for so many different situations, because you can modify it how you want, and most of the time it will work, obviously through a lot of experimentation. Okay, so let's also have a number to cross over. So if we say we only want to cross over 15, then we'll get 30 children out of that, and then the rest we can randomize. See, this is all the types of controls we can have. So I can say I want to pick 8 from the top, 3 from the bottom. I want to cross these over, say 15 times. I'll get 30 children, and the remaining 55 children I can leave to randomness. And this is getting closer and closer to reality, I think. I'm not sure. Alright, now let's create a list called the gene pool. Now the gene pool contains all the networks that have been selected. So here, these 11 will be added to the gene pool, but they'll be added to the gene pool in like a different amount of time. So I'll explain that as we go on further. We just need a counter called naturally selected to show how many were actually selected from the cross, how many were selected, and then how many we need to randomly generate. I'll explain that as it goes on. We need a population neural net that just keeps track of our entire population, and this is just for us to debug and see what's going on. Okay, so current generation, in each generation there's a population. Say in each generation there are 200 genomes, for example, and the genomes are each individual car in that population. And once we iterate through every single car in that population, we increment the generation 1 and we go on to the next one. So generation is a good way of tracking, say, how, I don't know, good your genetic algorithm is doing, because the lower amount of generations it takes, obviously the quicker it's evolved to reach your target. So the first thing we want to do in start is actually create the population. So we'll just say create population, and let's create that here, create population. Alright, so at the start what we want to do is completely randomize the population with completely random neural nets, just as we're doing now, and then after that, then that's where we start combining them. So in order to do that, let's say population equals new and net, and we can make it the size of the initial population. There we go. And we're going to have two methods here, fill population with random values, and we're going to pass in a population 0. I'll explain what that is in a second. And we're going to have a reset to current genome. So what these two are is, first it's going to fill out the population with random values, and then it's going to assign the first genome to the current car. So let's do the easier one first, which is private void reset to current genome. It's a mouthful, but it's very concise. And now we need to go back into the car controller, and we need to create a new method called reset with network. So we can pass in a network and then it can run it. So let's go here and say public void reset with network. Hold on, sorry, I'm just gonna adjust my mic. Sorry about that. Okay, so we're going to create this method called reset with network, and we're going to pass in a parameter of nnet. Okay, so we're passing in a neural net into the car controller, and then we're going to set it. We're just going to say this, the network of this car, we're just going to set it to net, and we're going to also call the reset method so everything restarts again. Yeah, that's about right. Now let's go back in here, and let's just say controller.reset with network, and I believe we're going to pass in the population's current genome. Okay, so basically what we're saying, the current genome is 0 initially, and what's going to happen is we're going to reset to current genome at the start, and it's just going to set it to the first network in the population, and then after this finishes, we're just going to say current genome ++ reset to current genome, and then we move on to the next genome. Alright, now let's create this fill population with random values. Random values, nnet, new population, int starting index. Alright, so basically why we have this starting index here is because we may only want to set a certain amount of this new population to a random value. Let me just write this up and I'll explain what I mean. So we'll say while starting index is lower than our initial population, new population starting index is equal to a new neural net, and we also need to say new population starting index dot initialize, and we already know that our layers and our neurons are in our controller class. So here we're just initializing this network with this amount of layers and this amount of neurons. So basically why we have the starting index, we'll set it to 0 here, so this will run like a normal for loop. It'll go through every element in the population and set it to a random neural net. But later on we'll use this same method, but we'll set the starting index to say somewhere near the end, because all of the values, all of the networks up to that starting index have already been created with crossed over neural nets, and the remaining population that hasn't been reinitialized, we're just going to randomize. So anything that hasn't been accounted for with crossover, we're just going to randomize. This is just to bring a lot of variety into our gene pool, and hopefully this works well. So now we're just going to say starting index ++, so we're going to go in an infinite loop, and note that if if we don't have any room left for the starting index, we give a starting index greater than the initial population, then there's no point of creating new random neural nets. So this is helpful in a way. Now, once we've done this, we need to actually have a way to increment the current genome, or this is going to just start off with a random neural net and just keep using the same network over and over and over again. So in order to do that, we need to have a depth function here. So let's just create that here. We'll call that depth float fitness and net network. And basically what this is once a car dies here, we're going to call depth, and it's going to come over here and it's going to say, all right, look, we died, now increment, and then do all this stuff. All right, so we're just going to say if current genome is lower than population dot length -1, population current genome dot fitness equals fitness. And basically what I'm doing, let me just explain in a sec. Alright, So what I've done here is I've brought in the population. The car controller has sent death over to the genetic manager and said, look, I've died. I'm going to give you my fitness and what network I'm a part of. And now we have this population network array. And we're just saying set this current genome's fitness to the fitness that was given, so we can keep a track of the historical of all the genomes up to this point, because we can't set the fitness here because this is changing. So remember last time we created a small little fitness float inside the actual nnet class itself. So we're assigning that fitness to the fitness of the car controller, because then we can actually save this fitness value, because we're going to use it in the future to order them in a descending order. Yes. Okay. Now, after we set the value, so we're storing it, we're going to say current genome plus plus. So we're going to the next car in the current generation. So in the current population, we're going to the next one, and then we're going to reset to current genome. So with the current genome, we're just going to set it back to the car. It's going to reset and do the whole thing over again, but now with a different nnet. Alright, now this is only going to work if the population, this is under the population.length -1. If it's not, then this is where we repopulate. But before we do this, let's go back into the car controller and actually tell our car when to die. So we're just gonna, let's just create a private void here, say death, and let's just say game object find object of type genetic manager dot death, and we're just gonna pass in this the overall fitness and the current network. And I'm just gonna use find object of type for now because it's not really a big deal. We're only gonna call this once every time it dies, so it's not really that expensive. Now let's go to on collision enter. Instead of passing in reset here, let's just call in death, because our death is going to handle the reset anyway. So we need to handle death there, and we also need to handle a death if it's actually too good. Here we go. So let's just say death. Oh, and sorry, no, this is if it's doing horribly. So this is to ensure that if the car has been alive for longer than 20 seconds but its fitness is really low, let's just kill it because it's not worth the living. And also if the fitness is way too good, also let's kill it because we want to, you know, just keep it going. Obviously this is a point where you would be like, okay, this is a car that works, so you would save it, save the weights to a file. I don't know if I'm going to be making an episode on that because that doesn't really have anything to do with this whole genetic algorithm stuff. That's just serialization. But yeah, I probably won't be making another video on that. Let's just see if we have called reset anywhere other than reset with network. And no, we haven't. So that means we've covered all our bases here on car controller. And if we run this, actually this should completely do random values, and at one point just stop working because it's exceeded the population length. So let's try that once this compiles. Alright, so let's go into our manager and set up a few variables. Alright, so the first thing we need to do is set the car controller. So let's just drag in the Jeep here, and all the mutation rates are all good. Number to crossover, let's just set this to say I actually have a screenshot here of the optimum controls. So the number to crossover seems to be 39. All the other settings seem to be fine, so let's just set this to 39. Like I said, the parameters are very important because like it's not that it won't work, it will just take a really long time to find the right car if you have wrong variables. You can't just turn the mutation rate up to 1, say, because then it will randomize everything. Or even if you had the mutation rate at 0.5, it would mutate half of the networks that come through, and that's just, it's just like, no, it's just not gonna work. Okay, so number to crossover is 39. That's all good. It doesn't really use that variable at the moment. So if we play this, hopefully we're not gonna get an error. Okay, so here we have one car, and you can see that the cars are doing different stuff. That means they have different networks, and this means our population is working. And at one point it should just repeat the same thing over and over again. Oh, and we have found a car that works. Yep, okay, we found a car that does the yeah, okay, here we go. Now it's exceeded the population limit and it's just going crazy. So we know that our genetic manager script works so far. Alright, now we need to move on to the actual fun stuff, because we've got all the maintenance stuff out of the way. We've got all the base script. Now it's time for the crossover and all the actual repopulation stuff. Alright, so let's create a private void, and we'll just call this repopulate, and this is gonna handle all of the repopulation stuff. So we're gonna make this one of our main methods here, and we're just this is gonna be like one of the more like management methods. It's not actually gonna do anything. So the first thing we're gonna do is we're gonna clear the gene pool, because we need to make sure nothing's left over from the last one. This is going to be completely scratch. Every generation we're going to clear the gene pool. Alright, now we need to increment the current generation, because this is a new generation now that we're repopulating. And we need to set the naturally selected back to 0. These are all the parameters that we're going to use to actually repopulate. So we need to ensure that these are set back to their default state. Alright, now the first thing we need to do is we need to actually sort the population. Now we need to sort them by fitness. So we need to make sure the higher the fitness, the higher they are up on the list of the gene pool. Not the gene pool, sorry, on the population. We're going to just sort the population array right now. And why this is useful is because obviously we have these parameters, best agent selection and worst agent selection. So we need to actually know which is the best and which is the worst. So let's go ahead and say private void sort population. And this is one big optimization point. I'm just going to use a bubble sort algorithm. Yeah, please don't kill me in the comments, but yeah, it's just a very simple bubble sort. Let's just create this. J equals I. J is the population of the length J plus plus. And if population I dot fitness is lower than population J dot fitness, and at temp equals population I. This is just a sorting algorithm. If you guys want to use another sorting algorithm, please go ahead. It's not going to make any difference. Just all we're doing here is we're ordering from highest fitness to lowest fitness. I believe this is bubble sort. I think so. I wanted to implement the simplest one when I started, so I could just write it out real quick. But here we go, sort population. Now we can ensure that all the population, everything in the population array is in order, so we can trust that. And now we can create a new temporary array, so we don't mess with the initial population array, but we're going to fill up this new temporary array. And that's why you would have been wondering, like up here, why are we just not using the original population array? Why do I need to pass this as a parameter? That's because we're creating a temporary one as to not tamper with the original one. Alright, so let's just call this new population. And we're just going to create a new method called pick best population. And when I say best, I'm lying, because I'm going to be picking some of the worst as well. Alright, so let's pick the best population. Now this is a slightly large method, but that's okay. So we're just going to return a net array. Okay, so the first thing we're going to do is we're going to create another temporary array, just so that we can work with it inside this method. And we're just going to make it of size initial population. And here we go. First, we are going to create a loop that will select from the top, and then we're going to have another loop that's going to select from the bottom. And when I mean select, I mean add to the gene pool. Now the gene pool doesn't have a fixed size. The gene pool is based on the fitness of the actual card that it's adding. So the idea behind the gene pool is that we say the top network is going to be added more times to the gene pool than the fourth best network. And this is because then when it comes to the crossover, we have a higher chance of picking the top network from the gene pool rather than the fourth best network. And that makes sense because the top network obviously performed much better than the fourth best network. And this is, you might be wondering, why not just pick the first one? And sure, go ahead, but the whole point of a genetic algorithm is everything is random. Like 99% of this process is random, and that's why it's like no one knows what's going on. Sometimes it could work amazingly well, and sometimes it could just be trash for a really long time. And yeah, we just gotta tweak the parameters to ensure that we have the best chance of it succeeding. Yeah, so let's go ahead and create the first loop. We're just gonna say int I equals 0, I is lower than best agent selection, I plus plus. And remember, our best agent selection is how much we want to pick from the top. Okay, so we need to go into the endnet and actually create a new method, and I'll explain why we need to create this method. What we need to say now, I'll actually write this out. This is going to be a bit confusing, but I think you guys will understand this. So we're just going to say population I dot, and this is where it starts to get a bit annoying. So we're going to say, and please tell me in the comments if there's a better way to do this, and I'm actually not sure if this is right, but this has worked for me. So I'm just gonna say this. Okay, so I'm gonna say new population, the current naturally selected. Don't worry, we're just gonna say naturally selected plus plus. And the reason we're saying naturally selected is because remember, the remaining ones that weren't naturally selected, all of those are going to be randomized. So we're just going to keep track of how many we're adding to how much we're actually taking from the initial population. Don't worry about the naturally selected thing. But what we need to do is we need to actually set the new populations naturally selected to the population I. Remember, we sorted population I and we need to set it. But the problem is, the way C# works is this will store a reference. And now this is where it gets annoying. This is going to store a reference. So whenever we mutate or change anything new population naturally selected, it's going to change population I. And if it changes population I, then any further calculations we do with population I won't be accurate because it's been changed in the past. And this was the source of a lot of headaches for me, because I was like, why is this not working? And I just realized, like, wait a second, I'm changing a reference. So I'm not like, yeah. So one of the biggest issues with this obviously is in the crossover, the population I reference needs to stay constant, because we're going to be picking out from the population I, say, like 3 or 4 times to reference the parents. But if the parents keep changing, then it's not going to work. So how do we overcome this? We need to create a new method in the endnet class. Say we need to call it initialize copy. Alright, so when we say initialize copy, all we're gonna do is we're just gonna copy the whole thing. And this would really annoy me if there was another method, like a really simple method to do this. The MathNet guys are quite smart, so I wouldn't be surprised if they do. So that's actually, why am I going in the car controller? Don't know. Let's go into the endnet class and let's create a public endnet initialize copy, and this will just return hidden neuron count, and this will just give back a copy of this endnet class that it's in. Alright, so this should be quite simple to do. Let's just say endnet n equals new endnet, and we need to copy the only things we need to copy are the hidden layers, the output layers, the hidden layers, the weights, and the biases. Yes, that's all we need. And everything else, the input, output, and no. We only need the weights and the biases. and we need to initialize the hidden layers. We don't need to copy them, we need to initialize them, because remember, this is just a list. The matrices inside this list doesn't actually have dimensions yet, dimensions assigned. So we need to initialize the hidden layers of the new neural net class, and we need to set the weights, set the biases to be the exact same as this one. And then hopefully we should have what we can say is a copied nnet class. So we need to create this list of matrix. Whoa, autocomplete does not like me today. New weights goes new list of matrix float, and see, we're going to create new list of matrix float, and we are going to actually initialize those as well. Okay, so what do we need to do? We need to loop through. Sorry, I'm creating the weights right now, right? Yes. Okay, so I'm gonna assign new weights to this new neural net class. So in order to do this, I need to loop through all the weights that I have right now in this neural net class. I should probably make it explicit by saying this dot weights dot count I++, just to make it clear for you guys. So I'm looping through the current weights in this class, and I'm going to assign that to this weights list, and then I'm going to assign this to this n, and I'm going to return n at the end, and hopefully we should have a copy. That was my logic. If I'm wrong, please tell me down below in the comments, because this will save me a lot of time in the future when I want to do something like this again. Okay, let's see what we need to do in order to copy this. Let's first we need to create the weight inside this weight class. So we can need a weight list, sorry, weight, because remember no new matrix, it's a matrix float dot build dot dense and dot row count weights I dot column count. Okay, so basically what we're doing is we're creating a new matrix with the exact same dimensions as this dot weights I. Okay, very simple stuff here. We're just creating a new matrix, and now I think I messed up. Hold on. This is literally programming 101. Scrolling through the oh no, I can't say from array, can I? No, I can't. Okay. Okay. I don't know if there's a simpler way to do this, because this is actually really painful. Now looking, like writing this again, I'm just thinking like, wow, was there not a better way to do this? But basically what we have to do is do a double for loop going through every weight in this and assigning it to every weight value in this. So basically we're doing a double for loop and getting every individual weight from this matrix and assigning it to this matrix here. Wow. Okay, this is this is bad, guys. This is bad. But like, let's just do it because it works. And it shouldn't be that expensive because our matrices are quite small. But obviously when we get higher, this is gonna into higher like layers and neurons, this is gonna get quite expensive. But I think the new Unity job system would love this type of task. Like the iJob Parallel 4 would work great with this. Like you would see a performance boost like 120, 200 times. But don't worry about that right now. Alright, so we're just going to say y equals 0, y is current weight dot column count y plus plus. Oh yeah, and guys, if you want to see a video on the job system, I was thinking of writing one for that anyway. But if you guys are interested, I can fast track that. Okay, so what I'm doing here is I'm setting current weights x and y coordinate inside the matrix to the current weights, like what we're iterating through's x and y coordinate. So we're just copying over the weights, basically. That's what's going on here. And now after this, once we've initialized the current weight here, right here, we're just gonna be like new weights dot add current weight. Wow, Okay, nice. Now that we've initialized the weights, we need to initialize the biases. So we just go new biases, new list of floats, and we're just going to list through all of the biases in the current neural net class. And we're just going to say new biases dot add biases I. And remember, biases is just floats, so we're just copying over a bunch of floats. I think there's a way to do this a lot easier, actually. I think I'm just being dumb. But add range. Yes, I think that works. Yeah, we don't need this. We can get rid of that. But if that doesn't work, then it's my fault. Then we can just say n.weights, and remember, n is our new neural net that we're creating here, equals new weights, n.biases equals new biases. And this is all because of a limitation in C# that I have to do this. But you know what, let's not get into that. Can't spell. Still can't spell. Here we go. And now there we go. And now the last thing we need to do is we need to say n.initialize hidden. Now we haven't created this method yet. Initialize hidden layer count, hidden neuron count. Remember, these values are actually coming from the parameters up here, and we need to return n. Now remember, I said that the hidden layers need to be initialized, like we have done somewhere here. We have initialized the hidden layers to have matrices of the amount of hidden layers containing the amount of hidden neurons that we've specified. So we need to create this method called initialize hidden to ensure that our hidden neurons are actually created correctly. So let's do that. That should be quite simple. Hidden and hidden layer count, hidden neuron count. This is the first time I've had actual proper names for variables. Usually it's just A, B, C. Alright, now all we need to do here before we initialize hidden is we need to say input layer.clear hidden layers.clear and output layer.clear, just to make sure everything we're working from a clean slate here. So, and what we need to do is we just need to say for input into I equals I, so then hidden layer count, no, that's just that, +1 because we're working with an integer value, I plus, and now we just need to build a matrix here. So matrix float, new matrix, new hidden layer, and we need to build a hidden layer. Don't worry, I'll explain what I'm doing in just a second. And we need to add that to the hidden layers dot add f. Alright, so basically what we've done is we've initialized the weights here, and the last thing remaining to do is initialize the hidden layers so that there are hidden layers, because remember, when we create the neural net, it's completely empty here. So we're creating new matrices. This is not f, this is new hidden layer, and we're just saying, okay, this n is the new neural net, and we're just saying initialize hidden using this many layers and this many neurons, and we're just looping through the hidden layer count and adding these empty matrices. Yes, we're just adding these empty matrices to this hidden layers here in this neural net class of hidden neuron count. It's basically what we were doing at the start here. It's nothing new. We're just initializing the hidden layers. Yeah, okay, now that we've done that, we went completely off from the genetic manager, and we need to come back here and we need to do this. So what we were doing is we were assigning the new population's naturally selected, like what it's currently at, to population I, but we're not setting it to population I, we're setting it to population I.initialize copy, and we're going to pass in the parameters controller.layers and controller.neurons. Alright, so now we have initialized the copy of population I, and we're setting it to this new population. Remember, naturally selected is just an increment that we're incrementing every time we add to this new population, and at the end we can pass this starting index. We can say starting index is equal to the naturally selected, and say the naturally selected is like 10 less than the new population's length. Then the last 10 haven't been initialized yet, so that's why we're just randomly initializing it here. That's why we're keeping track of this naturally selected integer, if you were confused with that. Now we also need to say new population naturally selected dot fitness equals 0. This also drove me crazy at one point, because the fitness here was equaling to the fitness of the last population, and yeah, it just did a lot of weird stuff when it was sorting. So just make sure to set the new population's naturally selected dot fitness equal to 0. So we're again at a clean slate. Alright, now this is the fun part. We say int f, random variable name, but don't worry, and we just need to say mathf round to integer sorry, population I dot fitness times 10. Okay, what is going on here? Basically, we're gonna say, alright, get the fitness multiplied by 10, and that's how many times we're going to add this current network into the gene pool. And this makes sense, because the higher the fitness, the more times it's going to be added into the gene pool. Therefore, the more likely it is to be selected to be crossed over. And you know, that's the whole the fittest survive and stuff like that. Alright, here we go. Int c equals 0, c is lower than f, c++, just a little loop going through f, and actually this should be f plus 1, but actually it doesn't matter. And we can just say genepool.add I. Okay, so we're not adding the neural net because that would be unnecessary, like references. We're just adding references, it's not needed. Instead, we can just add I, which is the index of the new population. Okay, so we're adding indexes to reference the neural net. So later we can just say new population, so to reference one, we'd just be like new population gene pool I, and that would give us a neural net. So yeah, we're just adding indices instead of references. Just saves some memory, but all the way I'm coding doesn't look like I care about memory anyway, but that's fine. Let's go into the next loop. So the first loop was to select the best ones, and then the second loop now is going to be to select the worst ones. So we're going to do another loop, and we're going to say worst agent selection I++, and int last equals population dot length. And basically what we're doing here is we're doing like an inverse loop. So we're looping through I is lower than worst agent selection. We're going higher up in I, but we're going to be taking away from the last. So we're just going to say last minus equals I. So it's just going to loop backwards up from the bottom of the array, because like I said, it's sorted from highest to lowest in terms of fitness. So now we're going backwards, and we're just going to copy this because it's the exact same code. And instead of this, it's just going to be lost. Instead of I, it's just going to be lost. And here it's also going to be add lost instead of I. And if I am correct, that is it. We have created our gene pool and our new population. Now we can just say return new population. Alright, and I think naturally selected, adding the naturally selected. I think I'm making a small mistake. Actually, what? No, I'm fine. Don't worry. Okay, so we're incrementing the naturally selected. We're all good. Alright, the next thing to do is to crossover. Yes, this is the real stuff. This is where stuff actually comes into play. Now, let's create a crossover function. Let's go into the repopulation, and let's just say crossover, and we're going to cross over the new population. And we're also going to mutate the new population. We're just going to create both of these because we're going to create both of these methods. Alright. Crossover. Okay. Public void. No, private. You don't need this anywhere else. Private void crossover. I'm going to get the array, and we're going to say new population. Alright, so we're gonna bring in this neural network array, and we're just gonna cross them over based on the gene pool. Alright, so for every crossover, remember, for every crossover there's 2 children that come out of it. So we have this variable number to cross over, and that's how many we're gonna cross over. Multiplied by 2 is gonna be the amount of population that comes out of that. Alright, so let's go for int I equals 0, I is lower than number to cross over, I plus equals 2 instead of 1, because we're incrementing by 2 each time, because we know that yeah, sorry, no, number to crossover, we're just gonna divide that by 2 here, so we don't have to deal with that later. So we're just gonna say plus equals 2, so any number to crossover is the actual amount that we're gonna get, so don't worry about that. So we're gonna say here int a index equals I, int b index equals I plus 1. Now, don't worry about that either. We're gonna get rid of that in just a second. Now we're gonna say if gene pool dot count is greater than 1, just to be safe, we're going to ensure that the a index is not equal to the b index. So what is a index and b index, you ask? Well, the a index is the index of the first parent that we're going to select, and the b index is the index of the second parent that we're going to select. And one thing we need to ensure is that the 2 parents are not the same, because if they're the same, then we're not going to get a new child. Alright, so all we're going to do now is we're going to do this weird, like, obviously there's 100 better ways to do this, but we're just going to ensure, I don't know why I called this L, but that's fine. We're just going to say, oh, because I already have used I, that's fine. Alright, we're just going to say a index is equal to gene pool random.range 0 gene pool dot count. So we're finding a random integer inside the gene pool, and the index that we're passing in is a random.range from 0 to the gene pool dot count. So we're basically finding a random element in the gene pool. B index equals gene pool random.range, same thing, dot count. Alright, easy. Now we need to say if a index is not equal to b index, then we have found what we have come for. We're just going to break out of this loop, and cool, we found a index and b index. Alright, now we need to actually initialize the 2 children. Alright, let's say child 1 equals new nnet child 2 equals new nnet. Now we're going to say child 1 to initialize control.layers. Sorry if I'm rushing, this time's getting a bit tight now. Neurons, I don't want to make this video go too long, you know. And we're just going to do the same thing for child 2 as well. We're just going to copy this, paste, we're going to initialize the next neural net as well. And we're going to say child1.fitness equals 0, just ensure everything is set back to 0. Okay, now this is the actual crossover method that we're going to be using. It's very simple. All we're going to say is we're going to loop through, and this is actually not right. Like technically crossover is meant to be a lot more subtle, but in our case, since it's a really simple problem, we're just going to swap over entire weight matrices. Right, so this is what we're gonna do. I'll show you. W equals 0, w is lower than child 1.weights.count, w plus plus, and now we're gonna have a little random.range that separates this. So we're gonna say 0.0 f, 1.0 f is lower than 0.5 f, and we have a 50% chance of going into this first, or a 50% chance going into the second. And we're gonna say, now remember, we're looping through each matrix in the weights array. So this is, we have the first layer here, second layer here, third layer here. Say for example, this is, according to this array, this is like weights 0 here, and this is weights array in between these two are weights 1 here. Okay, so that's what we're actually swapping. We are swapping these and picking and choosing one. So from, say, if we fall into this first if statement here, we're going to say child1 dot weights, the current weight matrix, we're going to say is, I'm going to pick it from the A index's weight. And for the child2 dot weights, I'm going to say B index dot weights W. So you see what I'm doing here is we pick the A index here, so that we put two different parents, and from the population we're saying, alright, I want the current weight matrix from A index, I'm going to set that to child1, and for child2 I'm going to pick it from the B index, right? And for the other if statement, we're just going to literally just swap these around, and now boom, now we've completely swapped these two, and now this time the child2 is going to get from the A index, and now child1 is going to get from the B index. See, it's completely randomized, and this is happening for every weight matrix inside this neural net. So this is it's going to have an assorted range between the A parent and the B parent, but we're swapping out entire matrices here. We're not swapping out individual weight values inside these matrices, because that's just going to get really annoying and complicated, and it's honestly too much fine-grained control for the situation that we have. Alright, so this is the crossover for the weight. If you have any doubts, concerns about this, please leave it down below in the comments. I'll be more than happy to answer any questions. Okay, now that we have crossed over weights, quote unquote crossed over, we need to now cross over biases, and it's the exact same thing. Honestly, just shouldn't even be a big deal to just do this. And actually, the biases crossover is actually a lot more accurate, because we're actually going to be doing individual values instead of entire matrices. Yeah, okay, so we're gonna have the same random no range thing here, and instead of weights, we're just gonna say here, we're just gonna say biases, and here also biases, and biases, and biases. And you might be like, wow, that's it, crossover? Yep. Obviously there's so many more crossover. There's papers on different methods of crossover, which one's best. This is so simple and it works, so why wouldn't you use this? Yeah, it's all based on the situation. You don't have to pick the most complicated crossover method for your problem if your problem doesn't have that many ways to solve it. If it's not that complicated, why would you pick something that's so nuanced? It's going to take you so much more training time, and it's just not worth it. Alright, so now that we have crossed it over, we can just say new population naturally selected equals child1, and we're going to increment the naturally selected because we've just added to the new population right now, and we're going to say new population naturally selected equals child2, and I've added to the new population again, so we need to make sure to increment the naturally selected again. Now remember, naturally selected, we have to increment it, or else when we randomize it at the end here, it'll overwrite all of what we've done so far. So we gotta make sure to increment naturally selected every time we add to new population. If I forgot to do that somewhere, please tell me down below in the comments. Alright, now the next most complicated thing that we have to do is the mutation. Once we do the mutation, you have just created your very own genetic algorithm. Now remember, the problem that I expressed last time in my video was that once we cross over, that's cool, we've spread out the genes, all good, it should be generating better results, but if we don't have a mix in the gene pool, then there's no point, because there's not if the initial population wasn't good, then no matter how many crossovers you do, you're never going to, you might never get a result that is satisfactory. So this is where the mutation comes in, and you keep the mutation rate very low, like you would have seen before. The number, it was very low, so that we don't mutate too often, or even the good ones will get weeded out by the mutation because it's too high. Now mutation. Let's do this now. Private void mutate nnet new population. I feel like I'm going a bit fast, but I think I have to. But if you guys have any questions, please leave it down below. I respond very quickly to all my comments. Okay, for int I equals 0, I is lower than naturally selected, I plus plus. Remember, we're only looping through the naturally selected in the new population because the rest of the new population haven't even been initialized yet, so why would we mutate them, right? Okay, now for each element in the new population under naturally selected, we're going to loop through their weights, and their weights is what we actually randomize. So we're just going to say new population I, because I is from the naturally selected, dot weights dot count c++, and we're going to say if random dot range 0.0f 1.0f is lower than the mutation rate. This is how we this is the randomness that comes into play. So obviously the lower the mutation rate, the lower the chance of this actually happening. And we can say new population I dot weights c equals mutate new population I dot weights c. Alright, so what is this new mutate function? Well, we're going to create a new mutate function that's going to take in a matrix and just randomize it. That's it. So always saying here, I should probably call this something else. Alright, mutate matrix. So it's going to take this weight. Remember, these are all neural nets that have been initialized so far based on the crossover. So these are the children that have been created from the crossover are being sent into this mutation. So the children of what have been created are what's being mutated. Okay, so you pass that in, and it's going through all the weights in those new children's weights, and we're going to go through each individual weight, and if it's lower than the mutation rate, then we're going to mutate that individual weight matrix. So let's create that now. We need to create matrix float mutate matrix float. We'll just call this A. So we're just gonna call this mutate matrix instead, and we're just going to return a mutated matrix. Alright, let's go int random points equals random dot range 1 a dot. Okay, I'm gonna explain this in a sec. This actually is kind of a confusing line. Actually, this is not even accurate. This is complete experimentation over time. Alright, so what I'm saying here is I don't want to mutate every single. This is trying. I tried to get closer to what the paper suggested by not mutating all of the weights, and I'm just going to be mutating just a couple of the weights. So this is what I'm doing here. So I'm going to be picking out of all of the weights in A, all of the values in A, I'm going to be picking a random amount of values inside this matrix to change. So the division by set, I could just leave this and it would pick one. I pick any amount of values between 1 and the actual amount of values within the A matrix, but I'm dividing it by 7 because that's what I found through experimentation. Actually seems like it's not picking too many, but it's not also picking too little. Alright, so let's just create a matrix float C, which is just temporary right now. We'll assign that to A, get that from A, sorry, and we're just gonna loop through the random points I++, and we're looping through the amount of random points there are, and we're going to find a random column and we're going to find a random row within this matrix, and then we are going to randomize that value. So let's first find the random column, random.range 0 to c.column count, and random row. There are multiple ways to mutate as well. This isn't the only way to mutate. I urge you to experiment with all of these methods, because you will learn so much more by experimenting than you will by just following set methods over and over again. Alright, so next thing we need to do is we need to say C random row, random column. We're going to say mathf.clamp, and we're going to do what I said before in the last video. Instead of setting a new value, we're going to be bumping it up or down by a little bit, because this makes more sense than just setting a new completely different value. We're going to be bumping it up or down a little bit. Alright, here we go. mathf.clamp c random row, random column, plus random.range, negative 1f, 1f, negative 1f, 1f. Alright, basically what we're doing here is we're getting the current value of the matrix, and we are adding any random number between -1 and 1, so it could bump up or down, but we gotta make sure it doesn't go outside of the range of -1 and 1, so we're just gonna clamp it. Don't know if this is right, works for me, so it must be right. Let's now return C, and you just created your own genetic algorithm. How do you feel? Okay, before we close up, we just need to do a bunch more stuff. We just need to say fill population with random values, and now this is what I've been talking about this whole time. We're going to pass in naturally selected now. So we're going to pass in this new population, which is our temporary population, and it's going to start at naturally selected, and it's going to go through all the networks that have not been initialized yet. Have not been initialized in the sense that they have not been added. Sorry, they have not been crossed over yet, or they haven't been added as a best network. So basically, if you look here, sorry, I think I didn't explain this correctly. If I say here and pick best population, I'm actually assigning the new populations naturally selected to the best agents. So I actually completely forgot to mention this. This is bad. But basically what I'm doing here is I'm transferring the best networks from the current generation over to the next generation unharmed. These are not changed in any way. I'm just handing over the best networks, because we don't want to lose the best networks. The best networks gotta stay. So we're passing over the best networks. The reason why we're not incrementing naturally selected over here is because we are not bringing over the worst agents to the worst genomes to the next generation. Why would we want to do that? But we do not want to lose. So for example, sometimes you would find the best car that works amazing, but through some crossover it can actually get worse. So why would you want to lose that car that did amazing, right? So we transfer these best agents over to the next generation unharmed, and we add them to the gene pool so that they get crossed over, and hopefully we can find a better version of these already best cars. So yes, that's why we're incrementing naturally selected here, because it's being added to the new population. We also increment naturally selected here because we're assigning to the new population. Alright, and now at the very end, all the cars that have not been initialized in the new population, we're going to initialize using fill population with random values. Sorry, I did not explain that well last time. Kind of slipped my mind. Alright, now let's say we're going to set the initial population back to the population. I'm going to say current genome is equal to 0 because we want to restart the whole loop again, and boom, reset the current genome, and you know that this repeats in a loop again. Now if I'm correct, we are done. So let me just close this and let this compile. Alright, so that just finished compiling, and let's go into our manager, make sure all our variables are set up, and let's actually just watch this, because you'll see the current generation and the current genomes going up as we play this, and hopefully we do not get any errors. And like I said before, let's increase the time scale so we can actually see this going up. As you can see the current genome. I should probably get back into here. We can see the current genome going up, and when we reach 85, oh okay, we seem to have an issue. Okay guys, so there was an index out of bounds error, and actually very simple issue. Had to look around a bit, but I got it. We're actually checking if it's lower than the current generation here instead of the current genome, so that's gonna be annoying to the script. So let's just save that and wait for it to compile, and hopefully this time when it goes over, it shouldn't be annoyed with us. Okay, so let's try this one more time. Hopefully it should work. Watch the current generation and current genome count, and when it reaches 85, the current generation should go up, and we should start again. As you can see, there are some cards that are already performing extremely well, and those are going to be part of our best agent selection, and they will be passed on to the next generation unharmed, so that we can build on the successes of the previous ones. I'm going to speed this up. And we can see here that the current generation is 1, and I believe our network had just solved it previously, but let's just see. And yeah, look, already our genetic algorithm has crossed over, it's saved the best ones, and it's done all this good stuff. And look, we've already found a perfect solution. The only reason that died before is because we have an if statement saying if your fitness is too high, just die. So here we know the best agents are being preserved, the crossover is working fine, the mutation's working fine. Alright guys, so it seems that everything worked fine. My computer just randomly crashed. But yeah, so I think this is going to be the last episode of the self-driving car series. So we created the neural net, we created the self-driving car controller, now the genetic algorithm script, and I think this is quite a useful video because there aren't many videos covering this topic, and I know like a lot of people are interested in this self-driving car and machine learning thing. So I'm happy if you guys found any value in these videos. I know these videos have been a long time coming, so I'm sorry about the delay. And yeah, it's been really fun working on this. So thank you guys for watching, and I'll see you next time.